All right, guys, welcome to today's class. Today, you're going to start Introduction to Geometry in ALPS textbook. It's very useful, and it can help you get into the AB and beyond. It's very, very useful. I recommend checking it out. All right. Anyways, let's just get started. These are the concepts that they use. Well, the got the problem, most of the problems from HMMT, SAMTS, ARMO, math counts, and AMCs. And here's some other resources to check out. And this is the basically extra bogus solution, side note, game, warning, important, and concept. It's these symbols. Alright? Okay, what's in the name? We're just going to be talking about each of these images tell a story. This book will share these stories with you, but before we tell these stories, we have to name our characters. Or it's an introduction to geometry. Draw 3 points and connect each to the other two with straight paths. Also, draw the circle that passes through all three of these points. Then draw a line through one of these 3 points such that the line goes inside the region you just formed and equally close to the two other straight paths you formed initially to this point. Draw a circle that goes through the one of your three first points that you drew a line through and through the point where this line hits the straight path that connects the other two of your first 3 points and through the point that is halfway between those two other points. If you can make such sense, and it's gonna go on or a little bit more, but if you can make such much sense of this problem, then you're much more of a careful reader than I am, right? I want special names for that. This is just terminology. I think you guys get it because you've done the AMC8 before, hopefully. But a point is just a random point in the point. I mean, it's just a point. All right. 1.2 is gonna say a segment. A segment is just a line connecting 2 points. I think we get it. Midpoint and marking segments with equal length. We use lines on the line to denote equal. So this, for example, if there's two small lines on each of these two segments, right over here. This one and this one. These two are the same exact thing. For example, just like this one. And the midpoint is just so that it's in between these two and in between the line. Alright? For example, XY, the midpoint is M, and it splits XY into two equal segments, XM and MY. And we have a ray. A ray is just a point, and that goes out to space with an arrow. It just goes on forever in one direction, not two directions, which is a line. A line goes in two directions. Segment is just part of this line. And then three concurrent lines, a concurrency is just when three lines meet at the same point. Collinear is just 3 points meeting in the same line, right? Now let's just get on to the exercises. Alice is thinking of a line. How many points on that line does she need to show Bob in order for Bob to know exactly which line she's thinking about? It's clearly very obvious, all right? Let's be honest, this is kind of very obvious. Why? Because for 1 point, you cannot determine which direction is the line going. For example, I have a line. Say this is the point. The line points right here, right? This is just going to be a ray. Why? Because you do not know the direction. You can go here, here, and you can continue the line the other way, right? So through 1 point, there can be infinitely many possible ideas, right? And so on. But if we have 2 points, there's only one possible line that goes through. All right? There, you can't go another way. The other way is the same exact line, all right? That's the important part to understand. If you have 2 points, you make a line. And then you later know that it's 3 points that make a circle, right? And so on. Now let's move on 1.2, 1.2.2. M is the midpoint of AB and N is the midpoint of BM. If BN equals 4, then what is AB? Alright? I'll let you guys try this question and tell me answer to chat. Shouldn't take long. It's a very simple, but I'll see if you guys get the idea. Okay, guys, let's get started with this question now. All right. M is the midpoint of AB, and N is the midpoint of BN. If BN equals 4, then what is AB? All right. First off, let's just draw a diagram so you guys can understand the picture. All right. N is the midpoint of BN. All right. Let me see. I think I have enough space. Let me see. Yep. So I'll just draw a line over here. Uh, this is BM. Say that's BM. And we know that it's M is the midpoint of BA. So that's our total line. Now, BM, the midpoint of that is N. So that's N. So BN is 4. That means the entire length of BM is 8, and double that is 16. And that's your answer, 16. All right? P, Q, R, S, T are on line K, such that Q is the midpoint of PT, R is the midpoint of QT, and S is the midpoint of RT. If PS is equal to 9, then what is PT? I was gonna try this question in 10 minutes through chat. Alright, let's get started with this question. P, Q, R, S, T are on line K, such that Q is the midpoint of PT, R is the midpoint of QT, and S is the midpoint of RT. If PS is equal to 9, what is PT? All right. Well, what is the same? Well, first off, Q is the midpoint of PT. We can just draw a line. Or R is the midpoint of QT, of PT. And S is the midpoint of RT. Q is the midpoint of PT. R is the midpoint of QT. And S is the midpoint of RT. I want PT. I know PS is 9. This is 9. Alright? Now here comes the very important part, right? This is a fraction of the segment, right? PT is the total, right? Notice that ST, let's know ST as the unit length. Call it X, right? We know that PS is equal to 9, so this means that PC must be at least a little bit greater than 9. That's for sure. Alright, then what is RS? RS is also X, and QR is 2X. This total gives us 4X for QT, which is half of PT. Or this means that this PQ is 4X. So we have a total of 7 X's and that's equal to 9, or Q at PS. So 7X is equal to 9, or X is equal to 9 over 7. How many are there in total? There's 1, 2, there's 7, 8. There's 8 in total. Wait, I'm not doing this quickly. Wait, hold up. PQRST underline, okay, so sorry, yep. Yep, I'm doing it right. So, and then from there, you just multiply by 8, since there's 8 cases of X's, and that's equal to 72 divided by 7. Right? Now let's move on to 1.2.4. Points A, B, C, D, E are 5 points on a line segment with endpoints A and E. The points are in order listed above from left to right. So it's like CD is equal to AB divided by 2, BC is equal to CD divided by 2, and AB is equal to AE divided by 2. And AE equals 12. What is the length of 80? I was going to try this question and turn this to chat. Let's get started with this question now. A, B, C, D, E are five points in a line with endpoints A and E, which are listed from left to right. That CD is equal to AB divided 2. Got A and E. Alright, A is 12. We have AB is equal to AB divided 2. BC is equal to CD divided by 2. And CD is equal to AB divided by 2. And then we get BC is equal to CD divided by 2. Alright. From here, you just notice that it's kind of confusing. How do we get CD is equal to AB divided by 2? And at the same time, BC is equal to CD divided by 2. Well, this is telling you that B is in between in C and D. And then boom, that's our configuration. I hope it's right, but we might be wrong. Or it's listed from left to right. And this means that it's a bit shifted over, right? We want BCU to CD divided by 2. So B and C are very close together, and D is 1/4 away. Alright? Be careful about the configuration issues. It kind of does not make sense. This is why there's a star. Star means that it's quite a tough question. It's a bit more tough, right? And it just requires you to have a knowledge about how the configuration works. But we know that BC is equal to CD divided 2. Let's make it a little bit more realistic. Oops. Make it a bit more realistic. Alright, and so BC is equal to CD divided by 2. 1/2 of CD. Alright, hope that makes a little bit more sense now. Since we have a diagram. Since AB is equal to AE divided by 2, that B is a midpoint, which makes sense. And then we have AB is going to be, which is equal to AE divided by 2, or 6. And now we just do the mathematics, right? Now we have CD is equal to AB divided by 2. Yep, that's AB divided by 2. And BC is equal to CD divided by 2. And then we get AE is equal to 12. This total is 12. So 80 is equal to 80 divided by 2. And that's 6, and that's 6. And then we have 80 divided by 2, that's just 3. And we want to find AD. Right? What do we want to find what BC is? CD divided by 2, that's 3 halves. And now we can find AD now. As 6 plus 3 is 9 plus 3 halves, or 21 divided by 2. And that's our answer. You could have not have a configuration and just straight up visualize it, but it does not have to be that accurate of a visualization. I'm gonna be honest. You didn't need a diagram to solve it, but the diagram just makes it a little bit more clear what's happening. Right? Now let's move on to 1.3, round and round. And that's about a circle. Mark a point on a piece of paper and label it as O. Use a ruler to find points on your paper that is 1 inch away from point O. If you draw all these 2 points, what figure would you create? And it's obviously that this figure is called a circle. What is the definition of a circle? A circle is a point where it has a center, which is a point, and the distance between the points on the circle and the point in the center are the same. Or it's like basically a line, you could say, so that the point, all the points on that line is equidistant from the center, right? In this case, that's x. And we have m and n, which are equidistant, clearly. And then p is also an equidistant. And if we have a line and that intersects a circle at exactly 1 point, that's a tangent. And can a line and a circle intersect at 0 points, 1 point, 2 point, 3 points more? At max, it can only intersect at 2 points. That's for sure. And then an arc is this portion of the circle or this portion of the circle. Basically, what the points separate into, right? Now we have a diameter, which is also basically a circle, circle's total span width, you could say, right? Or the largest distance or the widest point of a circle, right? And that's equal to 1.3.1. In the figure at right, identify whether each of the following is a secant line, chord, or radius, a diameter, or a tangent line of oval. If multiple terms are accurate, list all of the accurate items. All right, now this is basically uh definition fighting. So I'll let you guys try this question in terms through chat.
I can't see the question.
There. All right, let's get started with this question now. Some of you guys started doing this question, but haven't finished. But let's get started. CO. What is CO? CO is the line segment. If the arrows over here is very important. This tells you a lot of things right here. Right? For example, let's start with CO. CO itself is a line segment since there's no arrows at all. So we'll just say it's a radius, like most of you said. Now let's start with EF now. What is EF? EF is a tangent line. Remember, it's a line, right? Or we can just say a tangent. Since it intersects that at exactly one point. Right over here. Alright? And that's a line. If it has only one arrow, then that's a ray. Alright? Now let's move on to CD. CD is a chord. Why? You might say CD is also a line. Well, you're not wrong, but CD is not entirely in. CD is a line segment. C and D are points on the circle. That's a chord. You call that a chord. And what is AB? AB is the diameter, but also a chord. Chord is any line in the circle that it has 2 points on the circle. If you connect that, that's a line, which is also a chord. That's a line segment, and it's a chord. Right? It's also AB is a diameter, but also a chord, as it's in the middle of the circle, or it's in the widest point. Right? Now for CD, there's two arrows now. What does that mean? That means CD is not a chord no more, since it's not a line segment. It's actually a secant line. As you can review the definitions over here, you can say L is the tangent line to the circle if it intersects at exactly one point. Secant line if it's two. And then if it connects 2 points on the circle, that's a chord. And there we go. Now let's do 1.3.2. Suppose P is outside a given circle. Is it always possible to draw a line through P that is tangent to the circle? No proof is necessary now. You'll have the tools to prove your answers later in the text. All right? Let's go to try this question and turn it to chat. Let's get started this question now. Suppose point B is given outside. Is it possible to draw P its tangent to zero? Yes, indeed, yes. There are actually only two possible ways. Alright, you have the later tools. I won't prove it right now, but we will prove it later. Alright? So there's our circle, okay? It's not a perfect circle. Obviously, as you can see, there's a line cut from the top. I'm not the best circle drawer, but I think you get the idea. If you have a point P and somewhere in the plane, you can draw exactly two tangent lines that will hit the circle at exactly 1 point. But let me make it a bit bigger. There you go. There's one tangent line that goes here, and the other tangent line that goes here. Alright, this is only possible in two possible ways. Right? So the answer is just yes. Now, what's the maximum number of points of the intersection of a circle and a triangle? A triangle is formed by connecting 3 points with line segments. Let's give a try on this question and turn it through chat. Alright, let's get started with this question. It's quite obvious how you do it, alright? For noticing three, try to think outside the circle in this case, alright? How can we construct a story that has more than 3 points? I challenge you to find that. And notice that this circle and the circle and the triangle do not have to be the same size. Alright. This is our circle. We have a circle and we have a triangle. That's our circle and that's our triangle. How much points? This is clearly not really that much of the same size in this case. You guys are thinking about either this, or these are all tangent, or most obvious case, circle that encloses the triangle. There's only three possible points. But what if we think outside the circle? What if we make the triangle a bit bigger, so that it does not go outside to a point that it can never intersect, but it's just right in the sweet spot where it's not small enough that it fits inside the circle. It's not big enough so that it doesn't touch the circle at all. It just encloses it. Or that sweet spot? Oh, that sweet spot's over here. Now the circle and triangle intersect, but there's parts that are sticking out, right? And those parts we can see the intersection points. As you can see, there's 6 intersection points, and that's the maximum, right? 6 intersections. That's why we should think outside the circle. And we can actually achieve 5 sections if we do it this way. We can have a triangle and then we can have a triangle. It does not necessarily have to be normal. It's like a irregular triangle, just so like a scaling. We can have a circle hitting both sides, intersecting, and be tangent to only one side. And that'll give us 5 intersections, right? Now let's move on to 1.3.4. Two circles and three straight lines lie in the same plane. If neither of the circles or the lines are coincident, meaning the two circles are different and the three lines are all different, what is the maximum possible number of points at which at least two of the 5 figures intersect? Let's see how to try this question and turn it to chat. All right, let's get started with this question. All right. So here's what the diagram should look like. We want to maximize the intersections possible. All right. Here is the diagram. All right. We have two circles and three lines that intersect. Right. All of them intersect. Right. Now we just want to count intersections now. There's one intersection, two intersections, three intersections, four intersections, five intersections. This is the fifth one, sixth one, seventh one, eighth one, ninth one, 10th one, 11th one, 12th one, 13th one, 14th one, 15th one, 16th one. And we can squeeze one more into 17th. Next to maximum. If you actually did it all correct, right? Now we can just try again. And it really just depends on the accuracy of your diagram at this point. There's one, now there's two, and there's three, right? As you can see, it's basically just counting these parts now. There's one, there's two, there's three, there's four, there's five, there's six, there's seven, there's eight, there's nine, there's 10, there's 11, there's 12, there's 13, there's 14, 15, there's 16, there's 17. There you go. That's how you get 17. It's just basically make sure how you see you're doing the diagram correctly and you're counting correctly. That's the very most important case in this part. That's why there's a star. And it's also, you gotta visualize it, alright? So there's a total of 17 feet, 17 ways. The maximum number of points is just 17, alright? Just how you arrange your diagram is the most important part, and also how you count. Now, one more word construction, probably a segment. Classical construction problems are sprinkled throughout the book, and because a deep understanding of construction usually leads to a deep understanding of geometry. Yeah, the tools are compass and straight edges. Alright? Make circles on line segments. And that's what they used in the old days, when like 2,000 years ago they used it. Right? And we still use it today. And now we don't use ruler because we don't measure segments. And the reason why is because the ancient Greeks never had a unit of measurement in the first place. Alright? They used to have a unit measurement of stadiums. Just like something like 1 mile, 1 point something miles, or 10 miles or something. I forgot. But that's one of the units of measurement. And I don't think, frankly, it's not very helpful since like the small of alignment does not translate to a stadium very easily. Alright, now we have a user compass to find a point y on k such that AB is equal to x, y. You cannot use a ruler to measure AB, then use that to measure x, y. It's quite obvious. You just use a compass, measure this out, and then put it back over there. Simple as that. I forgot I do have a ruler and a compass. I'll keep that in mind. AB and MN, so find the AB minus MN. Yep, it's quite obvious how you're supposed to do it. And then you have select line segment AB plus MN. Oh, yep. And then so on. Alright. Then we find that a point MN from Q by opening our compass to with MN and using the radius to draw a circle centered at Q. As shown, this circle hits K at 2 points, and R and R prime, and so on. It just basically proves how can we do this. And then we have AB minus MN. What does it look like? It looks like that. And that's it. Now you want to find construct these following lengths. AB plus CD minus EF. 2AB AB minus 2EF plus 3CD. Well, you can just use circles as always. AB, you just draw, you can use the straight edge to, you can use a compass to measure out this length. And copy it and draw to a circle from that length. Then if you draw a point straight across through the middle, then you'll get the radius, the diameter, or 280. Or if you don't have the midpoint, you can literally just draw another circle of the same length, where the point on the circle, and then boom, you have the point, you have this point, draw a straight edge, and this side is just the diameter. Alright? AB plus C minus EF. Same exact thing. You have AB, draw that circle length AB, and then you got to draw this circle length CD, a much smaller circle, and then you get EF minus EF, and just copy this length. And then, so starting from here, you draw EF, which is around here, probably be around here, since it's a very big circle. And then this is your length. Alright? Or an AB minus 2EF plus 3CD, same exact thing. You'll keep on going. But just showing you how much ways you can make these segments using just compass and straight edge. Alright? And then the burden of the proof. Literally, we define a segment that direction that connects two points, and then we call it such a statement regardless that fact without proof an axiom, and axioms are also called postulates. And Euclid wrote it on his famous Elements, and Euclid is a famous guy. Euclid's Elements is the second most published book behind the Bible, right? And the all right angles are congruent, and these are all these axioms, right? And it uses these axioms to make theorems, and then a mathematical statement that is not an axiom but has not been proven false or true is called a conjecture, right? And the five is a very notorious one, right? Five is very notorious. There's many videos about this one. It's very interesting about what happens if you take it very if you take it illiterally, all right? It's not like if you think about there's exactly one point that passes through that point and never meets the first line. What if that point, that line, what if there's infinitely many? And what if there's none? And that gives you whole new planes of geometry, alright? It's a very interesting one, alright? And then we have the summary, alright? A point is, well, a point. Euclid called a point that, which has no part. We cannot do much better than that vague description. We typically denote points with capital letters, right? And how would you define a point? That's something to consider. A straight path is connecting the 2 points, right? Now a point on a segment that's halfway is just a midpoint, like middle plus point, and you do that midpoint. An equidistant is just equivalent or equal, or it's equid, and distant is the distance. If we start at a point, then head one direction forever, form a ray. Our starting point is the vertex of the ray. And we denote ray as AB with an arrow pointing to B. Alright? But the first point is the vertex of the ray. If we continue the line segment, a line segment would pass its endpoints forever in both directions, we form a line, or AB, with arrows pointing both ways. If this page was continued forever in every direction, the result will be a plane. Since we can move in two general directions, such as right, left, up, and down, on the plane we say the plane has 2 dimensions. We're living in 3 dimensions, or 3-dimensional, right? or three-dimensional, which is just as up and down, left and right, and I don't know what you call it, up and down. It's like a new dimension. I think I forgot. Well, we can just say if we have a coordinate plane that's x and y, and then we had got a z, right? Instead of all points that satisfy a specific condition is called a locus, right? And there's many different locuses, right? You come to learn it in high school, and eventually later along your math competition. If you continue to pursue all the way up to the highest level of mathematics competitions, you'll learn about the locus eventually. The set of all points that are the same distance from a given point is a circle. The given point is the center of the circle, and the fixed distance is the radius. We refer to a circle by using the center as by using the symbol dot in the middle and a circle that surrounds it. And plus add that to O. And this just gives you the definition we went over about. O is tangent line, just intersects at 1 point. Secant is just intersects 2 points but expands, goes on both directions. And then a chord. What is a chord? A chord basically is a line segment connecting 2 points on the circle. Diameter is just basically a chord, but it passes through the center of the circle. MN is the short arc that connects M and N. As you can see, this is just M. Oops. This is M. And this is N. The arc over here is the same as the arc over here. Well, it's not the same, but it's basically the same notation. And technically, we will only do it as a shorter arc, right? Then there's two ways to have an MN, right? And then we have an extra. We have on top of the first page an image illustrating a interesting geometric fact. In the image of the third table was the golden ratio spiral. You can clearly see over here. Golden ratio spiral. It's a very cool spiral. It's like a very, 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 very important spiral that's been seen in nature a lot of times, right? It's something to do with Fibonacci sequence, right? All right, now let's move on and see what it's about. Which is a rectangle that can be formed by dividing a square into another rectangle such that the ratio between the dimensions of the rectangle is equal to that of the original rectangle. Shown above is the golden rectangle ABCD with dimensions 1 and x. PQ divides the rectangle a square with side length 1, and then x where rectangle with the dimensions is x minus 1 to 1. The ratio of dimensions of ABCD is equal to the ratio of dimensions of BQCP. BCQP, we have 1 divided by x is equal to x minus 1 divided by 1. The positive value of x associated with the equation is 1 plus square root of 5 divided by 2, or 1.618034, or which we now know as the golden ratio, right? Or 5. And then so and then it goes on forever and it goes spirals and very cool. You can see it on Nautilus shells, and you can search up very beautiful patterns that basically imbued with the spiral, right? Like, it's basically we have a big circle, and then we have a small circle, and then we have a small circle. I mean, we have a smaller square. I mean, and it just goes on forever, basically bisecting this square, right? And so on. It repeats, and then you can connect the endpoints of either the square and to create an arc to spiral downwards. And you can see like this. Alright? Well, this is not the best way to describe it, but I hope you guys understand this. It's a very cool thing. And that's it for this chapter. All right. I'll see you guys next week. Thanks for attending the lesson, and I'll see you. Bye.